Recording has started now. So what are you seeing on the screen? Tell me.
Notes.
Notes, right? So once again, welcome to all guys to have our session. And then so till now whatever we have covered, right? So now today our class will start from this section, and that is about a loop as a magnet, right? A loop as a magnet, right? Just a minute. Loop as a magnet. So have you derived this equation and this result with the help of this magnetic field due to circular current loop at a point on its axis, right? Yesterday we have covered about this. Okay, now, and we will also go for Ampere's law today, right? So here it was, yeah. So now let's start. A loop as a magnet, right? We have a loop and it will act as a magnet. So look at here, this is a loop in which current is flowing in this loop, right? So because of this current in this loop, we are feeling that there is production of there is a production of magnetic field, right? So if we have a loop, and current is flowing in this loop, so because of this current a magnetic field induced here, right? So this is magnetic field. So in last class we had covered that if you keep your finger in this way, right, curl your fingers, so your thumb will give the direction of magnetic field, that is the scene over here. So this loop is in this way, right? So it is something like that. So it is acting as a magnet, right? It is acting as a magnet. This figure is equivalent to this, right? Okay, so that is why a loop as a magnet, so now it is north pole and it is south pole. We know south to north inside the and north to south, outside of the magnet, that's we know, right? Okay, so here magnet, this is the way. So you can see north pole side 2 and side 1 is north pole and side 2 is south pole, right? Side 2, this one, right? So this is the same. So now look at here, this is a loop and this is other magnet, right? This is other magnet. So because of this loop we have magnetic field here, and this, because of this magnet we have also magnetic field, right? So because of this loop, right, we have magnetic field, and because of this magnet we have magnetic field. So here you can see in the last class, or I think previous one classes, when we discussed about the interaction between two magnets, so one magnet and second magnet. So second magnet will apply force on one and one will apply force on two. It may be attractive or repulsive. The same thing is there. You can see here this loop is equivalent to this magnet, so I can replace this loop, right, can be replaced by this magnet. So this magnet here, that is north and it is south, so an interaction between these two will happen. So that's written here, the loop and the magnet attract each other. Obviously if it is north, it is south, it will attract to each other. This is attracting this in this way and this loop attracting this magnet in this direction, so that is attraction, right? So here the two loop attract each other. Simply suppose we have a loop and this is the second loop, and now you can see current is flowing in this way and current in the flowing in this way. So you can produce, because of this loop we can produce a magnet, so magnet will be in this way, south and north, and because of this we have a south and north. So it is north, it is south, so it will attract to each other, right? So The thing is very clear that if we have a two loop, one loop and it is second loop, so these two loop will attract each other if these loop contain, you know, currents, right? And direction is same, and if direction becomes just opposite, then thing will be different and it will uh, repel instead of attraction, right? So now it's clear. Now mathematics, we are going to use mathematics, how much force will be there, what will be magnetic field, right? Those all the things we will cover in this portion. So here look at the geometry. So geometry is not mentioned here. No, geometry is not mentioned here. Anyway, no problem. So we know one result from here, right? We know this result, right? This result because of we have a circular loop, right? And because of that, on axis at distance x, what will be magnetic field? We know from here, from the last result, right? Okay, so let's go ahead and try to understand. So magnetic field on axis, we know this thing, right? We know this thing, and this can be written approximated 2x cube because r is very small. So if r is very small, so we can neglect r, so only x will be there, so that is written here, right? So this is our final result. Okay, so because of loop on the axis, okay, let me admit someone is there. Okay, so now so now in last class we covered that on axis this will be magnetic field, so when we will approximate this we will get this one, right? It is similar with axis due to magnet, right? It is same answer we had discussed in our first class, that if we have a magnet, so what will be magnetic field on the axis, right? This was same thing that's we have covered here, right? So from here you can compare with capital M to current in is number of turns, and pi r square equal to capital M. So if you replace this by capital M, so that is same thing is here, right? So you can see here that is a small m, no, here it will be capital M, right? It is mistake over here, so you can write here capital M, right? So this result was there, this result we had already expressed, or we already derived in earlier classes. That means we have a magnet, and because of magnet at this place what will be magnetic field, that was the same thing, right? So here we have a loop, right? We have a loop and current is flowing in that, so because of this loop it's equivalent to magnet, it is equivalent to a magnet, right? So it is same thing, this is a magnet, so what will be magnetic field on the axis? It is similar to what we discussed in our first and our second classes, right? Okay, so same thing is here, m, that is magnetic dipole moment, we know. So this m is compared with this is our this result is come from the loop, and this result came from magnetic dipole moment, right? Or because of the magnet, right? So just to compare these two, so when you will compare, so this term equal to m, and that m, it is capital M, so m is this. So if we have a loop, so what will be magnetic dipole moment? So this will this one, I n pi r square. M is equal to I n A for any other shaped loop. Pi r square is what? Area. Pi r square is area. So magnetic dipole moment, that means suppose we have a loop something like that, and this area is A. So what will be magnetic dipole moment? And current is flowing I, and number of turns suppose 3. 3 turns are there. So magnetic moment will be I and 3 into area, right? So suppose it is a square, and current is I. So if question asks what is the magnetic dipole moment because of this current, so we will write simply I in, here is 1, so write 1, area that is pi, suppose it is A, sorry, not pi, a square, simply a square. The main is very, the thing is very clear, that what will be magnetic dipole moment. So magnetic dipole moment will simply current carrying in the loop, number of turns, and area. Area is area of loop, right? So this is the same. So by comparing these two results, we have this observation. Okay. So now unit of aim, dipole strength is ampere meter, we know. Okay. So unit of capital aim, that is ampere meter square. You can write from here. Okay. Like r square, you can find unit from here. I, that is current, that is ampere here, and r, that is meter, that is meter square. So as simple as it is. So now here you can see direction of the magnetic dipole moment, right? It is very important, right? So we have a loop and current is flowing in this loop in this way. So what will be magnetic dipole, direction? So you can see I in this direction. So aim is given by I into area, okay. So a is the unit normal vector of the loop, okay. So this is the loop, okay, and this is area A. So what will be unit vector of this area? It will be in this direction, right? So whatever the direction of the unit vector of area, that will the same direction of aim. Look at this one. I want to write bigger, like aim equals I, that is current, n, that is number of turns, and a is the cross section area. So I is constant, n is constant, sorry, a scalar quantity, and it is also a scalar quantity. So vector quantity a and aim is vector quantity. So direction of aim will depend on direction of a, right? So suppose we have this loop and this area is a, right? So we know that unit vector, right, unit normal vector of area. So if area is e, say its normal will be here. Normal means 90 degree from here. So this is direction of area vector, right? So same thing is here. If we have this loop, so unit vector of area will be in this direction. So that direction will be of magnetic dipole moment. So same thing is here, right? So here you can see here current is flowing in south to north, and here south to north in this way, right? Here it was, you can see anti-clockwise, and it is in clockwise. So aim is in this direction, right? So you can simply determine it from the magnetic field also, right? Magnetic field also, okay. So you can see there is a term over here to be determined by right hand rule, which is also used to determine direction of B. On the axis it is also from S, and it is all same thing, right? If current is flowing in this way, just to keep your fingers in the direction of B, curly fingers, and your thumb will give the direction of magnetic dipole moment. Similar thing, right? Okay, I think till now you have no doubt in it, right? So now question arises. Further we will discuss the application of these all the concept, and we will consider a geometry, that is solenoid, right? That is important, and generally a question asked from solenoid, right? So we will try to understand what is solenoid, right? So till now, have you any problem? Then ask me quickly, please.
No problem, sir.
Anyone?
No, sir.
No. Okay, then it's fine. So we will discuss about the solenoid, right? So solenoid is actually, this is a kind of geometry in which so many turns of the wire is something like that, right? So here what we had discussed, right now we discussed that we have a loop of n turns, right? Same thing we have covered in this section. So same theory will be applied in this solenoid. So solenoid is a geometry in which number of turns of wire exist like this, this is the number of turns, something like that, right? This is the way, right? This is circular one, these all are circular one. You can think about the spring, you know very well, a spring, right? So same thing is here now. So now you can see here, this is a solenoid, simple structure, right? And it may be a solid cylinder, hollow cylinder, yeah, something like that, circular loops right on the non-conductive cylinder. That means this is a cylinder, this is a cylinder on which, you know, this wire has wrapped, right? Wrapped, okay, wrapped means lapetna, okay. So now current is going in this way from this wire, and it will something like this, and it will come out from here. Current is going inward from this point and coming over from this point. And one thing we know, that if we have a loop, current carrying loop, then because of this current carrying loop there is magnetic field, right? The same thing is here. Because of this loop we have magnetic field, because of this loop we have magnetic field, because of this loop magnetic field, and direction of magnetic field because of the every wire, right, or every loop will be in this direction, right, in this direction. So this is the direction of magnetic field in this way, right? So whatever we discussed in the earlier concept, which is applied in this case, right, in the case of solenoid. Okay, so this is axis and this is radius of r, and this is direction of magnetic field. How, why magnetic field direction will be in this direction, we know very well, right? So now the second point, the winding the wire is in uniform direction of the magnetic field, same at all points of the axis. That is, if your wire is, you know, wrapped uniformly, then any point here, at any point you find magnetic field, the, you know, magnetic field will be same, right? That's written in the second point. That is, it will be constant on the axis. You have to think on the axis, right? B on axis, turns should be very close to each other, right? Magnetic field on axis, that means turns should be very close to each other. That means first turn, second turn, third, fourth, right? So this should be very near, it should not be far, right? In this figure you are saying that these two, you know, rod is far apart from one to each other, but no, in reality we have to keep very near to one another, right? So now here look at this is solenoid, right? This is solenoid, and now you can see magnetic field will in this way, and this is center, a point from here. This length is L1, right, and this length is L2, okay, and this is making angle theta 1, and this point is making angle theta 2. That means there are 2 points here and here, right? This point is making angle theta 1 and this point making angle theta 2 from the axis, right? Okay, so this is geometry which we will use here, right? So you know this result. Do you know this result? Because of one loop, you know this result. Tell me yes or no. Yeah, tell me.
क्या चीज है?
Though that result which was written there, we have already, you know, discussed about that result. So that's I'm asking, do you know this result? I am trying to show you. Yeah, tell me. You guys will not tell, right? Yeah,
No, sir.
look at here. Are you observing this same result?
सर सेम कहाँ है?
Yeah, look at, I will make sure, don't worry. Like this is a, you know, current flowing in this way, and because of this current, what will be the magnetic field here, right? Got it? Same thing we applied in circle. This is 2 points and we covered as all, right? So just to look at this result, right? This result. just I will compare with that one. And now there is, yeah, same result, but you will find here theta is different, sorry, minus here, right? Minus is here. So because of, in earlier classes what was there, theta 1 in this direction and other was one in this direction, right? But here both are in same direction, right? Both are in same direction, that means both are in anti-clockwise direction. So that is why one will be, minus. Okay, same result is here. So look at here, where n is the number of turns per unit length and cos theta 1 is equal to, and cos beta, and then minus cos theta 1 is equal to, minus of cos theta 2 equal to cos beta. So from here you can calculate from this geometry, right? This is beta, okay, this is theta 1, this is L1, right? And this is R, so from here you can calculate this one, isn't it? You can calculate this cos theta 1 cos beta, and that is minus cos theta 2. So when you will use this result in last expression, you will find this one, right? So that is mu naught ni by 2 cos theta 1 plus cos beta, same result it was there, that is this one. Like you can see here, this is a solenoid, and because of this we are calculating our result, and because of this we are getting result. So we can also, I can also add over here, suppose this is a loop, and because of this loop what will be magnetic field here, right? So similarly this is a loop and second loop is here, right? So because of this loop what will be magnetic field here, because of this loop what will magnetic field here, that's over here, right? Same thing is there. So from here you can see one more result I want to show you. Yeah, here. So it is not in terms of cos theta. So if you write these things in terms of cos theta, so here it is, if you put here, just to remove the just to put angle, same thing is here, right? Same thing, just to write dl, if you integrate dl overall, so dl is how much, 2 pi r, so 2 pi r going to cancel out, and mu naught will remain, and sine phi, integration of sine phi is going to cos phi, right? So same result is here, in other way, right? Same thing is there, mu naught ni by 2 cos theta 1. So it one turn because of this loop and other turn because of this loop, right? Are you getting right? There are two terms here, so one because of this loop and other because of this loop, right? Same thing, same result is here, right? Okay, this result because of this, that means we have a loop, and because of that what will be magnetic field at here at P point. So what was the answer? The answer is this one, we had integrated here. So when we will integrate, dl will become 2 pi r, so r cancel out, and pi and pi going to cancel out, right? And from here mu naught I upon 2r will be there, and sine phi you integrate, that will be cos phi, right? So here we have theta instead of that, so same thing is there. If number of turn in n, then we will multiply by n, right? So now I think it is clear, right? We will compare these results from there. So from here we calculated this one, that is same result, but only we replace theta 2 by beta. Use right hand direction, same direction due to loop, right? So now what is the thing? Now the thing is, if we have a solenoid, and this makings from here beta and this making from theta 1, so what will be result? So result will be plus cos theta beta 2, that's it. This is the magnetic field on axis, okay? So okay, now simple derivation is there, right? Same thing, whatever result is complete, over here, same result we can get from here. So I want to discuss in short. Like we know this result, right? We know this result because of one loop. So this is our one loop that had considered. So because of one loop, this will be there, right? So dx portion has taken from here. This result come from earlier one, this one you can see from here. That's I was discussing, that's I was discussing. Oh, where it was, let me check. Just a minute. Yeah, this result, right? This result on the axis. Okay, so here same result is there. You have to apply unitary method, and here assumption is from this is a point P, we are trying to calculate at this point, right? And this is a portion in which because of that portion we want to calculate magnetic field here, right? So magnetic field on the axis, right? So here because of dx length we have result because of one loop, right? And if number of turns are n, then we will multiply by n, but length is dx, right? So we will multiply by dx and we will calculate the magnetic field. So just to compare with that result, okay, and you will find here this result dB, okay, same result is. So now we will integrate. So integration is here, and then you will find dB dx and this. So other things mu naught I r square 2, these all will come out, right? So remaining portion is this one, r square plus x square under root 3 by 2. Okay, so just to integrate it, right? Just to integrate it. So when you integrate it and x is minus L1 to L2, right? You know integration under root r square plus x square dx. Tell me what will be the integration of this one? Yeah. Yeah, tell me guys. Integration of this kind of form. Don't tell. हेलो, क्या हो गया भाई?
हेलो।
या इसका इंटीग्रेशन मालूम है ना आप लोगों को?
मालूम है, याद नहीं आ रहा।
हाँ, नहीं याद आ रहा है, देखोगे जाकर अंडर रूट ए स्क्वायर प्लस एक्स स्क्वायर डी एक्स इंटीग्रेशन ओवर हेयर, राइट? सेम थिंग इज हैज अप्लाइड हेयर, राइट? ओके, so from here
Yes.
if you integrate this one in comparison of dx minus L1 to L2, will you put here? So L1 minus L2, you will get this result, same result is here, right? So it is simple derivation which you should know. Okay, right? So you have to think that theta 1 is from here and theta is this one, right? Theta 1 and theta 2. Instead of theta 2 you can write beta, that is this one, right? So you can write beta over here, right? So now we have a more case. So this is our result, main result of solenoid. You have to keep this result in your mind, and also theta 1 and theta 2. So now for ideal case means L is much larger than R, right? L is much larger than R. That means solenoid is very long, right? In comparison of this small r, right? So what will happen here? If L is much larger in comparison of R, right? So what will happen? So you can see in case of angle theta 1 be 0, you can see here theta 1. If it is very large, it will, suppose this goes to over here, so this will be go something like that, so this angle becomes 0 if it is too far, right? So theta 1 is 0, and theta 2 is this one, right? And it will also go too far, so this angle become 180 degree, right? So that's written here. So here it is mu naught in I, right? So if you have a long solenoid, very long solenoid, right? Very long solenoid. So because of the long solenoid, what will be the magnetic field on the axis? That will be mu naught in I N is number of turns of the wire over this, right? Okay, clear? Now second thing is, if material of the solenoid cylinder has relative permeability is mu r, then B will be mu naught mu r mu n I. Okay, so what is then? We have a solenoid and material is permeability is mu r or mu whatever, so that will come in multiplication, right? So result will be something different. Okay, now second thing, at the ends B will be mu naught Ni by 2, something like that. Like we have a solenoid, long solenoid, right? So what will be the magnetic field at the end, right? At the end, so it will be half of this one, right? Same thing, that means it is going very far, right? That is, we have a solenoid, like this, and that is very infinite, that means it is going to infinity. And here we want to calculate magnetic field at one end, right? So at one bit will be mu naught Ni by 2. How it will come? So from here you can calculate, right? One term is going to 0, so it will be mu naught Ni upon 2, right? Okay guys, so now we'll go ahead. So comparison between ideal and real solenoid. Okay, ideal solenoid is this one, right? So what is this figure? Try to understand, right? Okay, so this is x-axis, right? This is x-axis. Okay, this is x-axis, and this is magnetic field, right? And it is center of solenoid, this is center of solenoid. Okay, so what is the actual mean of that? That is, we have a solenoid, something like that, right? Something like that, we have a solenoid, right? This is our center. Okay, so from the center you can see at the end point we have magnetic field is, as you go towards the center, magnetic field going up, and then it will constant, and then at going towards the end of the center, right, end of the solenoid, it will fall down, and this it will become something like that, right? Something like that. But in real solenoid, this is something like that. So it is similarly like this. If we have a solenoid, something like that, solenoid, here it will be, so it is L by 2, half is there and half is there. So in the solenoid, magnetic field vary by something like that, right? ये फिगर समझ में आया तो बताओ, इट इज वेरी इंपॉर्टेंट. यहाँ से ग्राफ पूछ लिए जाते हैं कभी कभी, बच्चा को कंफ्यूज कर दिया जाता है.
नो सर.
नहीं समझ में आया?
नहीं.
क्यों भाई? Okay, no problem. Listen, that is center of solenoid. What should I make you understand, guys? Let me okay, whiteboard. I need whiteboard. Where is my whiteboard? Yeah, here. Now look at this. Was the line, and this is something like that, right? Something like that. This is the case. This is X, right? And here you are finding that this is a magnetic field B, right? Okay, and here the point is mu naught n I, right? And here there is a point here, that is mu naught in I upon 2. You can find there. This is center of solenoid, right? Okay. So just to draw a solenoid, right? Just to draw a solenoid in this way, right? So what we have covered till now here, that this is solenoid. So on in, if we have a length that is, you know, L by 2, minus L by 2 or plus L by 2, it is the origin. So what will be the magnetic field on the axis? That is, we know, mu naught in I. If it is no, if it is not too far, and if it is, you know, too long, then it will be mu naught in I. But when it is not too far, then we have a general, that is mu naught in I upon 2 cos theta 1 minus cos theta 2, something like that, you know. So here, just to look at, it is mu naught in I here, right? Mu naught in, that is the maximum, right? That is maximum, and maximum is here. Just to come, maximum is coming, something is constant, and then it falls down, right? Same thing is here, it is maximum, and after a point it is going to fall down, right? So what is that length, right? Dash length, as you know from figure, that is L by 2, and here it is minus L by 2. That means after a distance L by 2 it goes fall down, right? And you can see here, so one result we discussed, that if we have a solenoid and here, and if you want to calculate magnetic field at one end, if it is infinite, right? So here you will find mu naught Ni by 2 result. That's over here. So 1 minute, I want to show, yeah, here once again I'm trying to look at here in this figure. So just look at this one, and also look solenoid figure, so that you can compare from here, right? Yeah, right, you can compare here, right? Okay, so this is L2 annual in this case, right? So 1 minute, are this showing axis? Yeah, is showing axis. Look at here, this axis is x axis, look at it, x, right? It is x axis. Okay, fine. So now compare here, this is x axis, distance from the center, distance from the center means, look at here, distance from the center, right? This is a P point, so from distance we have a x distance here, right? So look at here, at the center we have magnetic field, this one, and if you go far from the center, B is still this, right? But after this distance B is going to decline, and this is the end point, that means solenoid is ending here, right? Okay, so this is your solenoid, right? So this is your axis. So at this point your magnetic field is mu naught Ni. At this point, everyone, you have a mu naught Ni, every point, right? But from here, if you reach near to end, this magnetic field going to fall down, and after end, this this will decline very fastly, right? Here you can see. So outside of this solenoid, there is magnetic field still there, right? But it is falling down. Okay, so that is the mean of this figure. But in reality, this figure is not only this portion is constant here, right? That means if we have a solenoid, so at the center here and here, only this section contains mu naught in I, right? But other than this point here, it will decrease, right? Here will be mu naught Ni by 2, mu naught Ni by 3, something like that. So it is going forward, right? So here also, So as you going far from the X, magnetic field going decrease in this way, and this is your solenoid, this is your end of the solenoid. So after this end of the solenoid, this will fall down something like it, right? So it goes to 0. So at this point magnetic field be 0. This is something like that, right? So now I understood this. Have you understood? Oh, what happens? Yeah,
Yes. आया हल्का हल्का
yeah, बोलो भाई.
आया
मुस्कान.
Yes, sir.
Got it. Okay, it's all right. Fine. So now there are some questions. So here a solenoid length 0.4 meter and diameter 0.6 meter consists of a single layer of these tons. 1000 tons हैं. Of fine wire carrying a current this. Find the magnetic field on the axis at the middle and at the ends of the solenoid. Clear? Right? You know formula. End पे क्या होगा और बीच में क्या होगा, right? Just you put the values and you will get your answer, right? Okay, so I am not going to discuss this question, that is already solved. So you will calculate. You will keep unit in your mind. You have to keep unit of magnetic field in your mind. So now we will discuss about Ampere's law. That is very, very important, right? So it is similar to Gauss law. It is similar to Gauss law, right? So I request you just to revise, okay? Just to revise Gauss law, okay? Gauss law. Or I can say if I discuss Ampere's law, you can revise Gauss law. Ampere's law मैं पढ़ा रहा हूँ तो तुम्हारा Gauss law भी एक साथ रिवीजन हो जाएगा, right? So just I'm telling you have to revise the Gauss law just to turn out the HC1 pages, and wherever you have studied, you can look at that portion, right? So now try to understand quickly about the Ampere's law, right? So here you can see this is current, 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 right? So it is something like that. Wire is something like that. Wire is something like that. So suppose this is wire. Suppose this is wire, right? Right. And current is I1, I2, I3, I4, I5. So in some cases it is inward, in some it is outward. And just to take this cross section. So if I take this boundary, so some current is going downward, in current some current wire current is going outward, right, or upward. Same thing is here. Here current is going inward, it is here current is coming upward, down, inward, upward, or outward, or inward, right, something like that. So because of current carrying wire, we know magnetic field, right? Because of this magnetic field come all around this current carrying wire, right? So Ampere suggested that if you integrate all around the loop, right, B dot dl, that will give mu naught into I, and I is enclosed, right? That is enclosed in the boundary, right? So it will not, I4 will not come in picture, I5 will not come in picture because it is out of the boundary, right? So whatever number of wires which are containing current inside the boundary, that will be considered in this section, right? We will not consider those current which is outside of the boundary, right? So that is the same. So that is the simple way to understand this theory, that you have to integrate this. So now you can see B is in this direction, and here I dl that is this length, right? So B dot dl, B is in this direction and dl will be in the direction of current, right? Current, right? So this is dot theta, that is dot theta, that is cos theta will come in the picture. So we will try to understand more about this thing, okay? So from here, justification of Ampere's law, you have to justify either it is correct or not. So look at here, this is a wire, carrying current I upward. So because of this current we have magnetic field in this way, and this is dl length, and this is r, and I is current, right? So look at here, in the limit del s tends to 0, we obtain b dot ds is equal to b ds. We have a limit that del s is very tending to 0. So look at here, in this condition b will be constant, right? And angle between these two will be 0, right? B and ds will be 0. Very, so look at here, b is constant, so b is coming out, so ds only is there. So b we know mu naught I upon 2 pi r, and ds, that is total length of this loop, will be 2 pi r, we know, so that will be mu naught I. So it is verification that b ds is equal to mu naught I, right? B, so it is a verification from here, right? So what will be the magnetic field? So magnetic field we know because of this, and we have a mu naught I, na, like in this case you have already calculated that you have a solenoid. So because of long solenoid, what will be the magnetic field at the center? Mu naught n I, right? So if we have a number of turns is 1, so n is equal to 1, then it will be mu naught I, mu naught into I, simple. So same thing is there, same thing is there, right? Same thing is there, right? Mu naught I, okay? So b dot ds, so b is mu naught I by 2 pi r, we know this thing. Magnetic field because of current carrying wire, mu naught I by 2 pi r, na. Suppose this is a current I, so what will be the magnetic field because of this? Just to read here, it will be mu naught I upon 2 pi r. This thing, we have a wire carrying current I, so because of this at perpendicular distance r, what will be magnetic field? So this is this much, right? And this, just to integrate, it will get 2 pi r, that is mu naught I. So now go ahead, so look at here this is a wire, right, carrying current I and coming outward, right, coming outward, and this is r2, this is r1, and look at here, let me erase this for clarity. So here look at, this is a loop, this is a loop, this is a loop here, okay, and this is also loop, and this is also loop till here, and then here, right? So this is the direction, right, loop. So this way, and here, and then here, here, and here, right? It is something like that, something like that, okay, something like that. So this is your loop, this way, this way, this way, this way, and this way, right? So this same thing here, right? So from here, what they are trying to show that, look at, so we will try to calculate b dot ds, right? So a b c d a, this is a, this is b, this is c, this is d, and then this is a. So this is our loop. The name of the loop is a b c d and a, right? This way a. So to calculate b dot ds, we have to divide these all the things part wise, right? For a b c d a, we have ab, bc, cd, and da, right? That means this way, and then this way, then this way, and then this way. So this is a loop, right? And this is a straight line loop, this is a straight line loop, and this is curve loop, right? So there are 4 portion, 1 2 3 and 4. So that's a written here, ab, bc, cd, and da. There are 4 portion, okay, there are 4 portion. So now it's a very interesting thing, just try to look at the figure. I want to zoom out so that you can see very clearly. So look at here, it's very interesting, try to understand. firstly, this is a wire, right? So look at, because of one wire we know if current is I here, and because of this we can calculate magnetic field here, right? But what will be magnetic field here? Here on the axis of current, same. So here magnetic field will be 0 because R is 0 here, right? Or something like that. So that no magnetic field. Suppose we have a wire I current is there, and here at any point here in this line, magnetic field will be 0. Okay, right? Same thing. So because of this wire, current here will be, magnetic field will be 0. Similarly, because of this we know, we had already covered this theory. If we have a this and we want to magnetic field here, so we can calculate. If it is theta, so we can calculate mu naught I theta upon 2 pi r, something like that, or 4 pi r. We know this thing. Okay, so because of this path we can calculate magnetic field here. Similarly, because of this it is in the same direction, so because of this it will be 0. Now because of this path, because of this, right? So same thing we can apply here. The angle between these two is this one, that is 360 minus theta. So whatever we have applied in this case, same result will be applied here, but theta will different, and R2 R1 also different. For this case we have R1, and for this case we have R2, right? So same thing is here, same thing discuss here. Look at here, 0, 2 will be 0 and 1, beta R2 theta, B1 R1 theta 2 pi minus theta, and this result we have already covered in the last class, right? So you will compare from there. Okay, so B dot ds, so B is 0 there, so 0, B is B2 there, so B2, and ds below how much? So ds is radius into angle, so R2 theta. B is B1 there, and ds, that is R1 into theta, that is 2 pi minus theta, you know very well. So B dot ds is this much, and this will equal to mu naught I, so that we will go ahead, right? And we know B1 is equal to this and B2 is equal to this, right? B1 is equal to this, equation become, so just use B1 and B2 in here, in this case. So just to put, you will find mu naught I. So hence proved that if we have a closed loop, right, closed loop, and whatever inside the current is there, right, because of that total magnetic field over this loop will be mu naught I. That is the proof, right? That is the proof. So here you can see that, loop is anyway here I should erase this one. Look at here, in this loop current was I here, it was I, right? I, so only I. So because in this loop we have a current I, so because of this I current, what will be the B dot ds? That will be mu naught I, because I was inside, right? So that is the thing. If inside, if it will be 2I, then answer will be 2I. So for verification of Ampere's law, we have taken this loop, and from there we calculated mu naught I. That's, you can see here, right? So that is the thing. So it will be applicable in any kind of the loop. In this case we had this one, something like this loop. If we have a something different kind of loop, here it will also applicable, but here a particular kind of loop has been taken to prove mu naught I in easy way. Okay, so here the field is given by this, very well, mu naught upon 2 pi r phi, and about the phi I have to say something about that, like Cartesian coordinate, right? Cartesian coordinate, like it is x, it is y, and it is t. So similarly we have a cylindrical coordinate, in cylindrical coordinate we have a r, right, B has Z, and B have phi. There are three things. Similarly, in cylindrical we have R, theta, and phi. R, theta, and phi. In a spherical coordinate. In cylindrical coordinate we have R, Z, phi, and in translational, sorry, yeah, coordinate we have a x, y, z. So translational, and then cylindrical, and then a spherical coordinate, right? So here we can write about the length can be written in this form. Length can be written in this form. So I try to make you something clear about this so that you can understand. So look at here. Just a minute. अरे भैया कुछ तो कर ले. Yeah, so we have a cylinder, right? We have a cylinder, something like that. So this direction is z direction, and this is a radial direction, and something like that. Suppose this is vertical cylinder, right? This is vertical cylinder. So this is z direction, and this is radial direction, and this direction is phi direction. Right? This is phi direction, right? Phi direction. So how to make you understand, that is also a question. Okay, देखो भाई, ये जो हमारा सिलेंडर है, ये जो एक्सिस है वो जे डायरेक्शन होता है, और ये जो रेडियस है, राइट, रेडियस का जो डायरेक्शन है वो रेडियल डायरेक्शन होता है, राइट. और ये जो फाई का डायरेक्शन है, राइट, वो फाई का डायरेक्शन समथिंग लाइक दैट, जो हमारा सिलेंडर होता है, राइट, तो सिलेंडर का जो ऊपर सरफेस वाला पार्ट देख लो, राइट, तो जो सरफेस वाला पार्ट देखोगे तो वो जो हमारा सरफेस है, जो सरफेस का नॉर्मल परपेंडिकुलर होता है वो हमारा फाई डायरेक्शन होता है, राइट. तो वो जो हमारा फाई डायरेक्शन होता है उसको हम ऐसे लिख सकते हैं, जैसे आर वेक्टर है मेरे को, ठीक, तो उसको हम लोग कैसे लिखते हैं, एक्स आई कैप प्लस वाई जे कैप प्लस जेड के कैप, राइट. उसी तरह से सिलेंडर में, राइट, यू कैन थिंक अबाउट व्हाट इज से, आई थिंक ये मैं एक बार आप लोगों को पढ़ाया था, राइट, जब मैं वैदिकुलम में पढ़ाया था, तो कॉपी थोड़ा होगा तो जाके रिवाइज कर लेना, राइट, मुझे याद आ रहा है वो मैं पढ़ाया था आप लोगों को. ओके, तो यहाँ पे देखो वही चीज़ लिखा गया, एक बार पढ़ लेना, राइट. अभी इन शॉर्ट में उतना सारा चीज़ मैं नहीं बता सकता, बट मैं बता रहा हूँ कि ये कहाँ से आया. तो ये जो आर है, राइट, अगर मैं इसको सिलेंड्रिकल फॉर्म में, सिलेंड्रिकल कोऑर्डिनेट में लिखूंगा तो डी आर आर कैप, आर डी फाई फाई कैप, right, if we have a cylinder, right, so in cylinder we have to write dl, right, dl in the form of this, so dr r cap, r d phi phi cap, right. And beta, here you can see, suppose we have a current carrying wire, right, okay, and here you will calculate magnetic field, right. So look at, okay, you can understand from here, this is z direction and this is r direction, and this direction will be phi direction. Okay, from here it will be phi direction, from here it will be phi direction, something like that, right. So here, you know this thing, mu naught I upon 2 pi r, and what will direction of b, that is the phi direction. And you know, because of the current carrying wire, magnetic field in this direction, so this is direction of phi. Okay, so ds, that is dl is here, dl can be written in the form of phi in this way. Okay, so that we can use here b dot ds, so b can be write b is this, and ds can be write r d phi. And what about r cap, so r cap is 0 there, right, r cap is 0 there. That means direction of magnetic field is 0 in the direction of r. Like suppose we have a current carrying wire, just to calculate magnetic field. So because of this current, we have a magnetic field in this direction only. In this direction, magnetic field is 0. That is why r, this portion has 0, because in that direction we don't have magnetic field. So that is why at the place of this we don't write this, we only write this portion, that is r d phi. So r d phi is there, and b is, we know this thing. So from here we can calculate d phi. How much, what will be the value of d phi? So look at here, mu naught I is there, 2 pi is there, r square is not there, and 1 r is there, right? So r will cancel out, so will be 2 pi r. So now we have a 2 phi. So what is the mean of d phi, right? So when we calculate d phi, so d phi will give mu naught I. From here you can see here. Okay, so one more thing is missing here. So d phi is equal to 2 pi. I want to hide here, यहाँ पे थोड़ा गलती है, ये यहाँ पे ऐसा होगा, राइट? What I can say, mu naught I, yeah, here should be mu naught I upon 2 pi, right? And value of d phi, integration of d phi, that is 2 pi. You have to remember, right? जैसे ये देखो ना, जैसे ये जो है हमारा, ये देखो, एक सेकंड, ये देखो, अगर हमारे पर ऐसे है और इसके चारों तरफ जा रहा है, तो ये जो डी फाई है वो कितना घूमेगा? तो 2 पाई घूमेगा। तो 2 पाई घूमेगा तो पूरा कवर हो गया। तो वही है, एक छोटा सा को डी फाई में बोल रहा हूँ, तो डी फाई को पूरा घुमा दिया तो इसका हो जाएगा 2 पाई। तो डी फाई का पूरा इंटीग्रेशन हमारे पास होता है 2 पाई। तो ये आ गया म्यू नॉट आई। तो यहाँ से भी हम लोग निकाल लिए कि भाई कि अगर एक क्लोज लूप है तो उसके कारण जो बी डॉट डी एस होगा, राइट, वो म्यू नॉट आई होगा। वो क्या होगा? म्यू नॉट आई होगा। यहां तक समझ में आया? बोलो। देखो फिर से मोटे तौर पे आप समझ लो, ये बोला गया कि ये बी है और उसको अगर एक लूप के साथ में ये करा दूं तो इसका वैल्यू म्यू नॉट आई आएगा। ये एम्पियर्स लाने बोला। इसको प्रूफ करने के लिए यहाँ पे दो तरह का, एक ये इस तरह से दिया गया, ऐसे था ना ये वाला क्वेश्चन, और इस तरह से ऐसे, राइट। यहाँ से एक करंट को दौड़ा दिया गया, राइट। तो इसके इस तरफ यहाँ पे मैग्नेटिक फील्ड जीरो होगा, इसके कारण जीरो होगा, इसके कारण होगा और इसके कारण होगा, राइट। तो अब क्या निकाला गया कि बी डॉट डी एस निकाल दो। तो बी डॉट डी एस निकालेंगे तो b1 इसके कारण बोल दिया गया b1, इसके कारण बोल दिया गया b2, तो b1 इंटू डी एस प्लस b2 इंटू डी एस ओवर इंटीग्रेशन, राइट। इसके कारण मैग्नेटिक फील्ड कितना होगा यहाँ पे? वी नो व्हाट, म्यू नोट आई अपॉन 2 पाई आर थीटा, समथिंग लाइक दैट, वो पुट कर दिया। ds क्या होगा? तो ये ds हम जानते हैं, ये ds कितना होगा? डेट विल डिपेंड ऑन द एंगल। सपोज दिस इज थीटा एंड दिस इज आर, तो ये डिस्टेंस कितना हो जाएगा? आर थीटा। उसी तरह से ये वाला, अगर ये r2 था तो यहाँ पे r2 हो जाएगा। ये r1 है तो r1 इंटू थीटा। अब ये थीटा मान लो दूसरा थीटा 2 है तो थीटा 2 लिख देंगे। तो यहाँ से वही चीज लिखा, b1 लिख लिया और ds से यहाँ से लिख लिया ये वाला r2 थीटा। तो इसको जब कैलकुलेट किया तो वहाँ आ गया म्यू नॉट आई। तो ये प्रूफ हो गया कि भाई एक लूप था, लूप के अंदर आई करंट था, राइट। तो उसके कारण जो बी डॉट डी एस का इंटीग्रेशन होगा वो म्यू नॉट आई होगा। यहां से प्रूफ करके दिखा दिया, राइट। सिमिलरली एक और इन्होंने ये लिया कि भाई देखो ये हमारा करंट कैरिंग वायर है और ये हमारा सिलेंडर, इसको बना दिया, राइट, इसको बना दिया सिलेंडर, राइट। और ये बोला कि सिलेंडर के अंदर आई करंट ऐसे भाग रहा है। तो ये बताओ कि यहाँ से ये सिलेंडर है, इधर से जो बी डॉट डी एस निकलेगा, बी डॉट डी एस जो होगा वो म्यू नॉट आई होगा। प्रूफ करके बताइए। तो सिंपल था, क्या किया कि भाई ये करंट कैरिंग वायर है, इसके कारण यहाँ पे मैग्नेटिक फील्ड क्या होगा? तो देखो ये आर डायरेक्शन है, आर इधर है, मैग्नेटिक फील्ड इधर होता है जो कि फाई का डायरेक्शन है। तो यहाँ से यही लिखा कि ये जो हमारा डी एल लेंथ है, यहाँ पे जो डी एल लेंथ है छोटा वाला, तो इस डी एल लेंथ को हम लिख सकते हैं डी आर आर कैप प्लस आर डी फाई, नहीं ये सिर्फ डी आर था ना, हाँ डी आर था, ये फाई कैप। चूंकि आर के डायरेक्शन में बी है ही नहीं, बी सिंपली इधर है, तो अगर इधर लेंगे तो उससे क्या कारण क्या होगा? 90 डिग्री बना लेगा, तो वो जीरो, तो इसलिए इसको हटा दिया गया, इसको बस रखा। तो ये हो गया आर डी फाई, राइट। इसके जगह पे ds के जगह पे, तो ds के जगह पे और b रख दो, तो b हमारा कितना था? म्यू नॉट आई अपॉन 2 पाई आर। इसको इंटीग्रेट कर देंगे, राइट। तो अब ये सब कांस्टेंट है तो ये सब बाहर आ जाएगा, डी फाई को कांस्टेंट करेंगे तो ये 2 पाई आएगा, यहाँ से यहाँ कट के ये आ जाएगा म्यू नॉट आई। तो यहाँ से भी प्रूफ हो गया कि ये जो करंट है राइट उसके कारण जो बी डॉट डी एल होगा वो म्यू नॉट आई होगा, राइट. सो दिस वाज द सिंपल प्रूफ इन दिस टू पार्ट, राइट. समझ में आ गई बात. तो कैलकुलेशन ऑफ मैग्नेटिक फील्ड ड्यू टू लॉन्ग स्ट्रेट वायर. तो यहां से देखो एक रिजल्ट बन के आ गया कि दिस म्यू नॉट आई इनक्लोज मतलब उस लूप के अंदर जो आई है उसके कारण ही होगा, राइट. एंड उसके बाहर जो करंट होगा उसको हम कंसीडर नहीं करेंगे, उसको कंसीडर नहीं करेंगे. तो सेम थिंग इज देयर कि भाई ये करंट कैरिंग वायर है और ये स्ट्रेट लाइन है और इसके कारण कितना होगा मैग्नेटिक बी डॉट डी एस, राइट. तो बी डॉट डी देखो यहाँ से निकाल लिया बी डी एल और डी एल कितना है 2 पाई आर. ये जो छोटा लेंथ है वो चारों तरफ को अगर इंटीग्रेट कर देंगे तो 2 पाई आर हो जाएगा. तो ये हो गया बी 2 पाई आर, इसके बराबर हो जाएगा म्यू नॉट आई. तो आई से यहाँ से भी, तो ये रिजल्ट देखो फिर से आ गया. यही रिजल्ट, ये रिजल्ट तुम निकाले थे ना पहले, म्यू नॉट आई बाई 2 पाई आर. तो ये एम्पियर्स लॉ लगा कर भी हम निकाल सकते हैं. एम्पियर्स लॉ भी अगर तुम लगा दोगे तो उससे भी म्यू नॉट आई बाई 2 पाई आर हो जाएगा, राइट. तो सेम थिंग इज देयर, मैग्नेटिक फील्ड ड्यू टू करंट कैरिंग थिन लॉन्ग पाइप. अब ये पाइप है, ठीक है, थिन लॉन्ग पाइप, इसमें करंट आई जा रहा है. तो बी डॉट डी एल फिर निकाल देंगे. तो बी डॉट डी एल 2 पाई आर दे देगा और आई टोटल अंदर कितना है, आई है. तो यही सेम रिजल्ट आ गया. कब, जब आर बड़ा है आर से, आर बड़ा है आर से मतलब ये जो हमारा रेडियस है राइट उससे ये जो आर है वो बड़ा है. लेकिन अब दूसरा केस आता है कि आर जब छोटा है कैपिटल आर से, मतलब कि ये जो पॉइंट है, ये जो पॉइंट है वो अंदर में कहीं है. यहाँ पे देखो, यहाँ पे राइट छोटा है, बड़ा नहीं है ये. तो उस केस में क्या होगा कि देखो हमको यहीं पे निकालना है, यहाँ पे निकालना है. तो अब करंट तो ऊपर है, देखो जब अगर तुम पाइप लोगे तो करंट ऊपर में रहता है. समझ में आ रही बात. ये हॉलो पंप है, जैसे तुम हॉलो पंप ले लो जिससे पानी जाता है. अगर वो लोहा वाला पंप है तो उसका जो करंट जो फ्लो होगा उसका सरफेस से फ्लो होगा. तो अंदर में तो करंट ही नहीं है, जो भी करंट है यहाँ है. तो अभी हम सर्किल बना लिए है ना, एम्पियर लूप बना दिए यहाँ पे. तो जब एम्पियर लूप बना देंगे यहाँ पे तो उसके अंदर तो करंट ही नहीं है इसमें. तो करंट यहाँ इनक्लोज जीरो है, इसलिए मैग्नेटिक फील्ड भी क्या हो जाएगा, जीरो हो जाएगा. तो ये देखो यहाँ पे ऐसा कर्व बना दिया गया. क्या बनाया गया, कर्व. इसका मतलब ये हुआ कि ये पंप है तो आर डिस्टेंस तक कोई भी मैग्नेटिक फील्ड नहीं है, बट आर के बाद करंट है, मैग्नेटिक फील्ड है और फिर वो धीरे धीरे डिक्रीज करता गया. बात समझ में आया. जैसे ये पंप है, ठीक है, पंप है और ये सेंटर है, तो सेंटर से आर तक मैग्नेटिक फील्ड जीरो है, मैग्नेटिक फील्ड जीरो हो गया. और यहाँ के बाद फिर वो मैग्नेटिक फील्ड आया, सबसे ज्यादा मैग्नेटिक फील्ड आर डिस्टेंस पे, मतलब जो सरफेस है उस पर, और फिर सरफेस से जैसे जैसे दूर जाएंगे मैग्नेटिक फील्ड घटते चला जाएगा, राइट. सो दैट इज द थिंग. ये यहाँ के अनुसार, इसके अनुसार है ना, बी जो है प्रोपोर्शनल है 1/r का ना, तो आर जितना बड़ा होगा बी उतना ही छोटा होगा. तो जैसे जैसे आर गया वो घटते चला गया. तो ये वाला फिगर इस तरह से हो गया, ठीक. तो उसका ये क्या हो गया, एप्लीकेशन हो गया. ओके. अब ये देखो इन्फॉर्म करंट डेंसिटी. करंट डेंसिटी का मतलब क्या हुआ, मैग्नेटिक फील्ड ड्यू टू करंट कैरिंग रॉड. करंट कैरिंग रॉड मतलब वो सॉलिड रॉड है. अब क्या है, ये सॉलिड रॉड है. तो सॉलिड रॉड में भी जब देखो आर से बड़ा हो, मतलब जब वो अंदर हो, आर बड़ा हो, लूप. देखो इसमें सबसे पहले एक लूप बनाया जाता है, राइट. तो देखो लूप कहाँ बनाया गया, बाहर में. तो बाहर में जब लूप बनाया गया तो सारा करंट उस लूप के अंदर आ गया. तो ये सेम रिजल्ट आ गया, राइट. मगर लूप अगर अब हम ऐसे बनाते हैं, लूप अगर अब हम अंदर बनाते हैं, यहाँ पे बनाते हैं, तो अब करंट क्या है, कुछ ही करंट इसके अंदर से जाएगा, बाकी करंट तो इस लूप के बाहर है, राइट. तो इसके लिए हमको है ना यूनिटरी मेथड लगाना पड़ेगा. दैट्स आई विल डिस्कस इन द नेक्स्ट क्लास. आई थिंक 1 hour has already covered, right. So now I will stop firstly recording. और लास्ट क्लास का रिकॉर्डिंग मैं ये नहीं किया हूँ, अपलोड नहीं किया, कल छुट्टी नहीं मिल पाया हमको.